Before 3D graphics became ordinary, companies bought entire computers to get it. Silicon graphics turned that scarcity into an empire. Its machines helped bring Jurassic Park's dinosaurs to life, while engineers and scientists used them to design the real world. By the late 1990s, SGI was a multi-billion-dollar company. Then its greatest advantage became ordinary. How did the company that proved the future could exist fail to protect it? Silicon graphics began with a bottleneck. In the late 1970s and early 1980s, interactive three-dimensional graphics demanded far more arithmetic than a general-purpose processor could comfortably deliver. A computer could store a model, but turning thousands of points into a changing image meant repeatedly transforming coordinates, clipping geometry, scaling it to a screen, and feeding the results into a display pipeline. The mathematics was known. The problem was doing it fast enough to feel immediate. At Stanford, computer scientist James Clark worked on a different answer. Do not ask the central processor to perform every graphics operation. Build specialized hardware for the geometry itself. His 1982 SIGGRAPH paper described the geometry engine, a VLSI system that distributed geometric operations across a pipeline of processors. It was not the invention of computer graphics, and it was not the first graphics processor in history. Its importance was narrower and more useful. It showed how a substantial part of the 3D transformation pipeline could be pushed into dedicated silicon. Clark and a small group from Stanford turned that work into a company. The Computer History Museum dates Silicon Graphics' founding to 1982 and records that its first graphics terminal appeared in 1984. Early accounts sometimes use 1981 for the beginning of the venture, but the institutional record provides the cleaner boundary. The research became a commercial company in 1982. The name of the first product family, Iris, hinted at the ambition. SGI was not trying to make a general computer that happened to draw pictures. It was building a computer around the act of seeing a model move. That distinction would become the company's first great advantage. It would also define the kind of advantage SGI later had to defend. An SGI system was powerful because its pieces were designed to cooperate. The graphics hardware accelerated operations that ordinary CPUs struggled to perform in real time. The workstation ran a Unix operating system. Its graphics software exposed a programming interface tuned to the hardware. And as the product line evolved, SGI moved from Motorola processors to the MIPS RISC architecture. The Iris 4D generation turned that combination into a recognizable platform. MIPS processors, custom graphics ASICs, IRIX and SGI's graphics libraries working as one system. That integration mattered because customers were not buying isolated benchmarks. An aircraft designer, a molecular scientist, or a visual effects artist needed a complete pipeline that could load data, manipulate a model, and redraw it fast enough to support decisions. SGI sold that experience at workstation prices, not PC prices. A contemporary Wired profile recalled an early 1984 SGI workstation costing about $80,000. The company reinforced the model by buying MIPS Computer Systems in 1992 for $333 million. Owning the processor company gave SGI more control over a central component of the platform. It was a logical move for a business whose differentiation came from tuning the whole stack. And the stack was difficult to copy cheaply. A rival needed fast processors, specialized graphics silicon, drivers, an operating environment, and professional software that users trusted. SGI could charge high margins because the alternative was often slower, less integrated, or simply unable to do the job interactively. This was the economic engine beneath the technical one. Graphics performance was scarce. SGI knew how to package that scarcity into a machine. For a while, every improvement in three-dimensional computing made the market for those machines more valuable. The company was not merely selling faster computers. It was selling access to a capability that much of the industry did not yet possess. By the early 1990s, SGI's machines had escaped the laboratory and entered the culture. Industrial designers used them to shape products. Scientists used them to visualize data. Government laboratories and engineering organizations bought high-end systems for simulation. And in visual effects, SGI became a symbol of the new digital production pipeline. Jurassic Park gave the company an unforgettable association with computer-generated imagery. But Hollywood was never the whole business. A 1994 Wired profile reported that entertainment represented less than 10% of sales at the time. The scale was already substantial. Fiscal 1993 revenue had passed $1 billion. In fiscal 1996, before fully consolidating Cray Research, Silicon Graphics reported about $2.8 billion in revenue and $245 million in net income. By fiscal 1997, annual sales were approaching $3.7 billion. In 1998, the company still employed roughly 10,500 people worldwide. SGI's influence also moved beyond its own machines. Its proprietary IRIS-GL programming interface had given developers a way to reach SGI graphics hardware. But a proprietary interface tied the software ecosystem to one vendor. In 1992, SGI engineers Kurt Akeley and Mark Siegel published the first OpenGL specification. The design standardized access to graphics hardware while leaving hardware-specific implementation work to vendors and Windows system integration to the operating environment. An industry review board gave the interface governance beyond a single product line. OpenGL was a strategic triumph. It made advanced 3D programming more portable and gave SGI's graphics ideas a path onto other platforms. It also revealed a paradox that would become more important with time. SGI's empire had been built by tightly coupling specialized hardware and software. OpenGL helped make the software interface less dependent on that coupling. That did not hurt SGI while the company's hardware remained dramatically better. But standards become most powerful when alternatives catch up. And by the middle of the 1990s, the alternatives were learning quickly. The threat to SGI did not arrive as one machine. It arrived as a collection of technologies becoming good enough at the same time. Intel processors kept improving. Windows NT moved upward into professional computing. Graphics accelerator companies pushed 3D performance into far cheaper systems. The PC ecosystem brought enormous manufacturing volumes and a growing software base. At the high end, Sun, Hewlett-Packard, and IBM could spread engineering and support costs across much larger businesses. OpenGL itself made this changing market easier for developers to navigate. Its portability meant that the same graphics concepts no longer required an SGI workstation. John Carmack later recalled that by the mid-1990s, OpenGL made it practical to move graphics code between iRIX and Windows NT, while consumer-level 3D cards were rapidly improving. The point is not that OpenGL destroyed silicon graphics. That would turn an industry transition into a morality tale. The more defensible conclusion is that the standard helped separate applications from one vendor's hardware at exactly the moment competing hardware was becoming useful. SGI saw the transition. It did not simply sleep through the PC revolution. By 1997, contemporary reporting was already describing pressure from Windows NT and commodity systems. In 1998, SGI announced a major strategic shift toward Intel processors, planned to spin MIPS back out, cut roughly $200 million in expenses, and reduce its workforce by about 1,000 positions. The company was trying to move from a proprietary processor future toward an industry-standard one. The problem was timing and economics. SGI had built an organization around systems that were expensive because their integration was rare. As standard processors and graphics accelerators improved, the price customers were willing to pay for that rarity began to fall. The moat was not erased in one product cycle. It was being converted from a machine into an interface, from custom silicon into commodity components, and from a closed performance advantage into a competitive market. As the lower end of the workstation market became more dangerous, SGI tried to expand in both directions. One direction was software. In 1995, the company moved to acquire Alias Research and Wavefront Technologies in a stock transaction reported at roughly $500 million. The logic was understandable. If graphics hardware was becoming easier to buy, the professional software that created digital content could become a stronger part of the value chain. The move was also defensive. Microsoft had acquired Softimage and was pushing professional graphics toward Windows NT. The other direction was upward. In 1996, SGI agreed to acquire Cray Research in a deal reported at about $740 million. Cray brought one of the most famous names in supercomputing, plus access to customers whose problems remained too large for ordinary workstations. If commodity computers were attacking from below, the high end looked like safer ground. Again, these were not irrational decisions. They were attempts to preserve differentiation as the center of the market shifted. But each move increased the number of businesses SGI had to integrate while its original workstation economics were weakening. It now had processor operations, professional software, graphics workstations, and supercomputing assets. Cray also arrived with losses and restructuring demands. SGI eventually sold the Cray product line to Terra Computer in 2000. Terra then adopted the Cray name. The acquisitions did not single-handedly cause Silicon Graphics' decline. They did something subtler. They raised the organizational and financial difficulty of executing a platform transition that was already hard. SGI was trying to become less dependent on the very workstation model that still paid most of its bills. It needed the old empire to finance the search for a new one. That is a dangerous moment for any technology company. The future has become visible, but the business that can fund the move still belongs to the past. The late 1990s turned SGI's strategic problem into an operational one. Revenue stopped behaving like the revenue of a growth company. Layoffs followed. Leadership changes, product transitions accumulated. The company experimented with Intel-based systems and Windows, then concentrated increasingly on high-performance servers and Linux. Itanium became part of the roadmap, yet the legacy platform could not simply be switched off. SGI's own 2003 annual report captured the contradiction. Research and development investment was moving toward newer growth areas, including the Linux and Itanium-based Altix line, while investment in traditional MIPS and IRIX products was declining. But those traditional products still supplied the bulk of company revenue. The numbers show how little room the company had to make the crossing. Revenue fell from about $2.75 billion in fiscal 1999 to $2.33 billion in 2000, $1.85 billion in 2001, $1.34 billion in 2002, and less than $962 million in 2003. Headcount moved in the same direction, from more than 9,000 employees in 1999 to about 3,700 in 2003. By then, the company reported that it had been operating unprofitably for 6 fiscal years. It pointed to a weak technology market, intense competition from much larger companies, product families in transition, and management and employee turnover. This is where the familiar story that SGI simply refused to abandon proprietary technology breaks down. The company did move. It moved repeatedly. The deeper problem was that changing architectures also changed the reasons to buy from SGI. A Linux server built from Intel processors could benefit from SGI engineering, but it entered a market where customers could also buy processors, memory, operating systems, and clusters from many other vendors. The new strategy reduced dependence on proprietary components. It also reduced some of the exclusivity that had supported SGI's old margins. SGI had 2 futures at once: a declining proprietary platform that still generated cash, and a more open platform whose economics were far less forgiving. When Silicon Graphics entered Chapter 11 in 2006, its own restructuring documents offered an unusually candid diagnosis. The company said investments made in the late 1990s had produced less than expected. The technology downturn of 2001 and 2002 cut customer spending and reduced the money available for research and development. Larger competitors could spread costs across higher sales volumes. Product delays and dependence on third-party suppliers weakened launches. Commodity computer clusters, including systems assembled from suppliers such as Dell, advanced faster than SGI had expected in parts of high-performance computing. And the company's expenses did not fall as quickly as its revenue. SGI still carried a cost structure built for a much larger business. Debt added pressure. So did legacy real estate. A long-term headquarters commitment in Mountain View remained costly even after much of the campus was subleased to Google. The restructuring disclosure estimated that the arrangement was still consuming roughly $10 million in cash per year before bankruptcy. These factors belong in different categories. Commodity hardware and open platforms were structural changes. Delays and management turnover were execution problems. The technology recession was an external shock. Debt, overhead, and property commitments amplified the damage. None alone explains the collapse. Together, they made recovery progressively harder. SGI filed its first Chapter 11 case on May 8, 2006, and emerged that October. Existing common equity was canceled. The reorganized company kept pushing toward Linux, industry-standard Intel processors, clusters, and large shared memory systems. Technically, the strategy was coherent. By 2008, SGI was explicitly describing standard components and open-source software as a way to lower cost while adding proprietary technology only where it could still differentiate. Financially, there was little margin for error. The company ended fiscal 2008 with about 1,600 employees, only about $40 million in unrestricted cash and investments, and another large net loss. SGI had finally embraced much of the commodity world. It had not escaped the economics that world imposed. On April 1, 2009, Silicon Graphics filed for Chapter 11 again. Rackable Systems signed an initial agreement to buy substantially all of SGI's operating assets for about $25 million. A bankruptcy auction raised the price. The court-approved transaction was reported at $42.5 million in cash, plus the assumption of certain liabilities, and the acquisition closed on May 8th. Then came a detail that can make the company's history look more continuous than it really was. Rackable did not become a subsidiary of the old Silicon Graphics. Rackable bought the assets. 10 days after the closing, Rackable Systems changed its own name to Silicon Graphics International. Later SEC filings explicitly called the seller Legacy SGI. The operating technology, customer relationships, and brand could continue, but the legal lineage had changed. That successor was itself acquired by Hewlett-Packard Enterprise in 2016. If the story ended there, SGI would be another famous workstation company absorbed by cheaper standards. But its legacy is more specific than the survival of a logo. OpenGL remains a maintained Kronos graphics specification. XFS, the high-performance journaling file system that originated on SGI's IRIX operating system, remains part of the Linux kernel. And the broader engineering idea behind SGI's early success is now ordinary computing practice. Use specialized parallel hardware for graphics, expose it through a stable software interface, and let applications rely on acceleration without knowing every detail of the silicon beneath it. That does not mean a modern GPU is simply an SGI geometry engine with more transistors. The architectures and corporate lineages are far more complicated. The legacy is conceptual and infrastructural, not a claim of sole invention. SGI built a computer around graphics. The industry learned to build graphics into every computer. So the company did not fail because it could not imagine the future. It had helped demonstrate that future, and it repeatedly tried to adapt to it. What changed was the economic location of its advantage. Specialized 3D performance moved from an expensive integrated workstation into standards, commodity processors, mass-market accelerators, and open systems. SGI did not miss the future. The future unbundled SGI's advantage. And once that advantage was no longer scarce enough to pay for the empire around it, even one of computing's most influential machines could become obsolete as a business.